Hello, and welcome to the OpenXR Masterclass. The plan for this part of the talk today is to spend a few moments introducing myself and then discussing the basic object handle types in OpenXR. At that point, we'll have the background to explore how OpenXR models interaction. Then we'll take a deep dive into OpenXR application structure and API usage. If you have any questions as we go, you can post them in the stream and they'll be forwarded to me. I encourage you to download these slides either now or after the talk at the URL on the screen. The slides include complete speaker notes, and mentions of functions and types are all linked to reference pages and the specification, which can be helpful as a reference. My name is Ryan Pavlik. I've been working in the VR realm since around 2009. I've been involved with the OpenXR working group since the first official meeting in 2017. I was elected specification editor for the working group in 2019. I am a principal software engineer at Collabora, where I work on customer projects in the XR team and contribute to Monado, which is our open source OpenXR runtime. There are a number of important object types in OpenXR, which are represented by handles. These are the main handle types. All handle types except XR instance have a parent handle type. In OpenXR, destroying a parent handle also destroys all handles that come from it. For example, if you destroy a session, that also destroys the associated spaces and swap chains. If you destroy an instance, that destroys all the handles of the types shown here, since they all come from the instance. In addition to handles, there are two additional types known as atoms. They're not objects, and they don't have an explicit lifetime. They're just coded numbers that represent some fixed thing in the runtime. The one you'll work with most often is a path. An XR path is a number that corresponds to a string representing a semantic path. Although these have no explicit lifetime, they only have meaning in the instance they're retrieved from. Do not save or reuse these between runs. An important part of immersive technology is interaction. Before we get into the details of how an OpenXR application is structured, let's take a few minutes to look at how OpenXR models interaction, since it might be a new approach for you. OpenXR focuses on the actions that a user takes in your application, instead of on the buttons and controllers that are used to perform those actions. This is an important part of the hardware independence provided by OpenXR. In OpenXR, an action is a semantic or meaningful bit of interaction. It's something that you do. Grab object and teleport are examples of names for actions. Actions that should be available in a given context or environment are grouped into action sets. For example, you might have an action set called menu, one called gameplay, and one called driving. You can have one or more action sets active at a single time. So you can have additional gameplay. So you can have gameplay and driving both active. you do not need to duplicate actions between action sets or create additional action sets, combining others. There are several types of actions available. Boolean is essentially a button action. It is either on or off. Float actions are things like an analog trigger. Vector 2 are two-dimensional floats, things like a thumbstick or trackpad. Pose is a special kind of action that's a tracked object. Frequently, these represent hands. Finally, haptic actions are an output action allowing you to provide rumble or tactile feedback to the user. Once you've established which logical actions a user of your application will make, you can then customize how they actually perform those actions for the hardware that you're testing. This is done using suggested bindings for interaction profiles. For each controller type that you've tested, look up its interaction profile. These are listed in the specification and cover a number of well-known devices. Additional interaction profiles will be added through extensions. For each device you test with, you submit actions and their suggested bindings for the corresponding interaction profile. The suggested bindings are the logical part of the controller that you'd like to use to drive that action. The specific button, for example. You can suggest multiple bindings per action in a call. For instance, both your left and right hands, and thus your left and right controller, can both cause action grab object to happen. The binding path that you'd like to suggest is a hierarchical string like /user/hand/right/input/select/click. This is on the screen. Here you can see that we are referring to the select button on the right hand controller, and specifically the click operation of that select button. For the last two path levels, there are naming conventions and standardized names that are detailed in the specification. All these paths are listed in the interaction profile definitions in the specification. It's important to only suggest bindings for interaction profiles matching devices that you actually tested. Your application will still be able to run on other runtimes. Those runtimes may automatically map your actions to the controller available. As runtimes continue to advance, you can expect that these rebindings will increase in quality and can be updated independently from your application. They may also provide an interface for the user to customize how the actions are mapped to their controller, and perhaps even share these bindings with other users. Remapping or rebinding can also be done to improve comfort or accessibility to support a wider array of users. This part of the specification design is strongly influenced by the success Valve has found with their similar Steam Input and SteamVR input action binding and remapping systems. You will typically set up actions, action sets, and suggest bindings for interaction profiles in a single block of code during the startup process of your application. This model is actually enforced by OpenXR. Before you can use actions in your main loop, you need to make a call to attach your action sets to a session. This tells the runtime that you're all done setting up your actions, action sets, and suggested bindings. You're going to use them with this session, and that you're not going to change them anymore. This does make your actions and action sets immutable. You can't modify them after this point, and there's a special error code that you'd get if you tried to do that. If you happen to be writing an editor for a game engine where your users would be likely to want to edit their actions as they make their game, the solution for editing actions is that each time you must tear down the session, the actions, and the action sets, then recreate them in order to modify them. This seems like a pain, but there's an important reason that the action setup is done all up front. The main reason is rebinding. We want the runtime to be able to provide the user with the maximum ability to configure how they're interacting with your application right away. To do this, your application must provide the runtime with the maximum information about its interactions as early as it can. That way, when a user launches your application, if you do not have suggested bindings for the hardware that they have, the runtime can remap the actions automatically, or pop up a UI that lets them map your specified actions to the hardware that they have available. This would happen behind the scenes and goes unnoticed by your application. You just get compatibility. If you were able to add actions and action sets later on during program execution, instead of just upfront, it would then interrupt the flow of your application if rebinding needed to be done a second. Additionally, if a runtime supports sharing bindings between users, you'd be able to compose a binding that supports all actions only if the action setup is done all at once. Otherwise, for example, if there's an action or action set that's only used in the last scene or two of your game, then a community-created rebinding might be incomplete if that scene was not yet reached or was on a path that wasn't followed, making it less useful in general. To make this a bit more concrete, I've gone through the sample Hello XR application that's in the OpenXR SDK source and summarized the actions and bindings that are used there. The initialize actions member function is where these get set up if you want to look at the source code on your own later. All these actions are in a single action set because the application is very simple. Additionally, all of these actions are specified for both the left and right hands. This uses the concept of subaction paths. This lets the user both perform an action with either of two hands, but also let you know which one hand actually did it. It's similar to the SteamVR input concept of restrict to device, in case you're familiar with that. The four actions in Hello XR represent a variety of action types. We have grab object, which is a float input, hand pose, which is a pose input, quit session, which is a Boolean input, and vibrate hand, which is a haptic vibration output. After creating that action set and those four actions, it's time to suggest bindings. There are a number of calls in HelloXR to suggest bindings. I've picked a few of them for 3 different interaction profiles to illustrate some key points. This first call uses the interaction profile KHR Simple Controller. Unlike most other interaction profiles, this does not correspond to any particular specific piece of hardware. Instead, it's a generic, lowest common denominator sort of device that can be mapped to a wide variety of hardware. There are a few things to notice here. Overall, as you'll see is a pattern, the suggested binding path for the interaction profile, starting with user hand left, will be marked as for the sub-action path of user hand left, and similarly for user hand right. In this application, all actions can be done with either hand, but you would not see this pattern if you had actions that could only be performed by one hand. One point about the simple controller is that its select input is Boolean. It only has on or off. We're binding grab object, which is a float input, to user hand left input select click, which is Boolean. This is fine. The runtime will automatically convert that Boolean value to a float 1 or 0. There are conversion rules that are specified in the specification for these common simple cases. The second example is the HTC Vive Controller. Here you can see we've bound the grab object action to a different path. That's because the Vive Controller has an analog trigger rather than a button simply labeled select. This analog trigger, which is a float, is now being suggested as our binding for grab object. The runtime will not need to convert a Boolean to a float. The grab object action will get something that's not just limited to 0 or 1, but might be anywhere in that entire range. The last example of suggested bindings is the Oculus Touch controller. The Oculus Touch controller has a float squeeze input. It can report how hard you are squeezing using a floating point value between 0 and 1. The grab object action will get a value anywhere in that range, just like the analog trigger on a Vive controller. Additionally, only the left controller has a menu button. So in this case, we're only suggesting a binding for the left hand for the quit session action, which uses the menu button. We're not suggesting a binding for user hand right for that action, and that's okay. Now that we've covered interaction, we'll move on to the last segment, the structure of an OpenXR application. Here's the outline. We'll go into all of these in more detail. First, you get started by configuring and creating your XR instance. Next, you find out where and how to run. This involves looking up a system ID atom and using the view configuration type enum. Then you set up your interaction in OpenXR. This is done using action sets and actions, as we just discussed. Finally, the last setup step is preparing the immersive experience by creating your session, attaching action sets, creating reference and action spaces, and creating your swap chain. The body of your application consists of advancing the frame loop, responding to input, and handling events. When you create an instance, you first need to choose which extensions you want. Very similar to how Vulkan works. In order to make an OpenXR application, you need at least one extension enabled, and that's a graphics binding extension, to choose which graphics API you will use to render. You can find out which extensions are all available on the system that you're running on by using XR enumerate instance extension properties. However, if you don't have any optional extension usage, only required extensions, you can just proceed to create the instance and ask for the extensions you need. It will either succeed if they are all available, or return an error if one or more is not available. There's also a facility for API layers. Like in Vulkan, these provide a way to hook behavior and change the behavior of functions. These can be configured outside of your application through environment variables or similar to make sure that the loader will automatically load them. However, if your application wants to load some explicitly, you can enumerate which ones are available before you create an instance. Similar to Vulkan, there's an application info struct that you should fill out with your application name and engine name version so that runtimes can identify your application. Finally, XR create instance takes that information and hands you an instance handle, which you will use in the rest of your app. You use XR get system to find out if your desired form factor is available. OpenXR 1.0 natively supports, without extensions, stereo head-mounted displays, as well as handheld mono, magic window style augmented reality. However, not all runtimes will support both of these form factors of devices. Part of the app startup process is asking if there is a system of the form factor you need available. There are a few possible outcomes. The form factor that you asked for might be available, in which case you'll get a system ID. It might never be available if the device that you're using can't do the form factor that you asked for. If you're on a desktop and you asked for Magic Window AR, for example. Or finally, it might be temporarily unavailable if it's perhaps not plugged in, or if it needs to transition to a different mode in order to be used in that way. For example, a smartphone with a slide-in VR headset is a device that can be used in multiple form factors. And the stereo head-mounted display form factor would be unavailable when not in the headset. Once you have a system, you set up your view configuration. This is where mono, stereo, or even more views come in. If you support more than one view configuration, you can use XR enumerate view configurations to find out which ones are supported by the system you've chosen, to make your determination of which one to use. No matter which view configuration you use, you will then call XR enumerate view configuration views to get the details of each of the views for your view configuration. Each view configuration has a known number of views. Mono has 1, stereo has 2. The Vario quad view, which is provided by an extension, has 4, and so on. These are well-known values listed in the specification. Once you have an instance, you can get your interactions set up. These are your action sets and actions. We have already discussed most details of action setup. You create an action set with XR create action set. You create all actions, no matter the type, using XR create action. After creating all action sets and actions, you can suggest bindings. Call XR suggest interaction profile bindings once for each controller type, or interaction profile, that you've tested, passing as many action bindings as you like. If you call XR suggest interaction profile bindings more than once for a single interaction profile, only your last successful call will be considered by the runtime. Note that actions and action sets are children of instance, but they can only be used when attached to a session. The next major handle to create is your session. You'll first want to get your graphics binding ready. Depending on which graphics API you use, there will be a Get API Graphics Requirements call that's specified by that extension. You need to call that before calling XR Create Session, or you'll get an error. This provides useful information on how to configure your rendering in order to get the rendered content onto the display. You then create a graphics binding struct. These are also specified by the graphics binding extensions, and they're all chained on via the next pointer on XR session create info. I haven't talked about the next pointer too much, but similar to Vulkan, OpenXR structures contain a type field as well as a void pointer field named next that allows you to add additional structures to the parameters of a call as a chain. This is mostly used for extension functionality, but there are a few cases in the core specification where using the next pointer is required, and this is one of them. In addition to the graphics binding struct, you must also provide your system ID from earlier. This goes in the XR session create info. Once you've called XR create session, you then need to attach your action sets to it by calling XR attach session action sets. As we discussed earlier, this makes your actions, action sets, and suggested bindings immutable. To interact with tracked objects, you use XR space handles. There are multiple ways to get these handles. Several spaces are known as reference spaces. You access these using your XR session and an enum. 3 of these are local space, view space, and stage space. There are additional ones added in extensions. Stage space can be considered a bounded area, standing play environment. Local space is a seated play space. View space is for control and rendering things that are head-locked. To get an XR space from these enums, you use XR create reference space. Another kind of space is an action space. To create these, you use your XR session and a pose action. The result is an XR space, just the same as with create reference space. So your use of them after creation is mostly the same. For both of these types of spaces, session is the parent handle. Additionally, for both of these space types, you can specify an additional fixed transform at handle creation time. XR locate space is the call used to find the transform from one space to another. Note that you never just find the pose, position and orientation, of a space. You always find the pose or location of a space with respect to another space. For example, you don't track just your hand. You track your hand relative to local or stage space. To render your graphics, you will need to create a swap chain. You will obtain your graphics API specific formats through XR enumerate swap chain formats. Then you'll call XR create swap chain one or more times. Once you've created a swap chain, you will access the graphics API specific handles or references to the swap chain images using XR enumerate swap chain images. This is a slightly unusual call. You will pass an array of extension-defined structures to this core OpenXR function. You will want to save the information that comes back from this call to use every frame. The contents of those structures specify, in a graphics API specific way, where to render your image. Within your application's frame loop, there are 3 functions with frame in the name that control the life cycle of a frame. XR wait frame is a scheduling call. When you call it, it blocks and does not return until the runtime determines that you can proceed with head pose dependent simulation and rendering. It also provides you with the predicted display time for the frame you're about to start working on rendering. You'll use this time in all of your calculations and all of your space locations. XR begin frame is executed by your application to mark the start of rendering or GPU usage for that frame. Finally, XR end frame submits the frame for display. It takes a parameter of type XR end frame info, and you populate the XR end frame info display time using the predicted display time from XR wait frame. If your application is using pipelined or multi-threaded rendering, there are some more detailed timing requirements that are important to know. XR begin frame and end frame calls must be ordered as if they were single-threaded, although they may be called from any thread. You can have at most one simultaneous XR wait frame call being executed at a time, and each XR wait frame must be eventually matched with a unique XR begin frame. They come in pairs. Each wait frame has a begin frame, and each begin frame has a wait frame. Additionally, any XR wait frame call will block in the runtime at least until the previous frame's XR begin frame call has been made. Between begin and end frame, once it's time to actually render, you'll need to use the swap chain that you created earlier. XR acquire swap chain image does not give you permission to write to the image, but it does get you the index of the swap chain image you will use this frame. You can use this index to find the graphics API specific handle that you enumerated and cached earlier with your XR enumerate swap chain images call. XR wait swap chain image must be called before writing to that image. It's typically called immediately after acquire. However, as an optimization, You may look up or create your command buffers using just the index from acquire swap chain image before waiting for the compositor to release the image for writing by your application. XR release swap chain image is what you call when you're all done rendering, right before calling XR end frame. XR end frame implicitly uses the most recently released swap chain image for displaying to the device. When you are doing your rendering, you need to render for the predicted display time and for the predicted head pose at that time. The predicted display time comes from wait frame, and XR locate views is how you look up the predicted view pose at that time. It works very similarly to XR locate space. Now that we have an application that can render, we should get input to make it interactive. XR sync actions should be called once per simulation frame in your application. It specifies which action sets should be active for that frame and updates all non-pose input data in those active action sets. Any action sets not specified in the most recent XR sync actions call are considered not active and will not get updated data. After you sync actions, then get the action data. Actions that belong to an inactive action set will return that they are not active. Additionally, actions might become inactive and might not get data if your session is not focused for privacy and security purposes. To get action data from actions, you will use get action state calls. There's one of these calls for each type of action. Pose actions are a little bit different. They continue updating all the time, not just at XR sync actions time, because tracking is latency and time sensitive. To get the data from a pose action, you will usually just create an XR space for it, and then use XR locate space. Only the active-inactive state of a pose action is controlled by XR sync actions. Typically, you'll process most of your input either before you call XR wait frame and begin frame, or after you call XR end frame. There's one other main item that we haven't yet discussed. There is a per instance event queue that contains a range of events. This queue must be polled on a regular basis. Typically, polling once a simulation frame is a good idea. XR poll events requires an instance. However, many events only happen during a session. These events can describe changes to the interaction profile, continuity of reference spaces and tracking, changes in the session state, and other things. You provide an XR event data buffer to XR poll events, and the runtime populates it with an event of some other type. You have to make sure you set the type field to XR type event data buffer before the call, and then when you get it back from XR poll events, check that type value and reinterpret that structure accordingly. Each event type has its own documentation in the specification. Thanks for your time. Hopefully, you found this introduction to OpenXR an exploration of the structure of an OpenXR application to be helpful. I've put a number of resources on this slide that you can follow for additional information. If you have questions that we can't get to during this session, please feel free to drop by one of the community locations for the OpenXR group and leave a note there with your question. I or someone else in the community will be happy to respond.
Thank you, Ryan.
Thanks.